Okay. Hi, afternoon, everyone. Okay. Let me try and zoom in. Hopefully that's good. Oh, I'm so sorry. Okay. So today, I was hoping we can just do some examples from assignment 2. We'll do some stuff from assignment 2. Then we will talk more about the symmetric group. In particular, we want to talk about symmetric and alternating groups. Okay. And then if we have time, another thing we should talk about is commutators. Okay. So, you know, we have kind of three sessions of approximately 40 minutes each, and I'm thinking each one should take about that long. Good. So let me just remind you, assignment 2 is due next Wednesday at 5. And let's take up a few questions from it, or at least similar questions. Okay, to get an idea of what's happening. Okay. Okay, so let's start with question 8. We're looking at, let's see, how do I use this? So we're looking at this group GL2F, where F is Z mod 2Z, and GL2F is then the 2x2 matrices A, B, C, D, such that A, B, C, and D are in Z mod 2Z, and AD minus BC is not equal to 0. Okay, and then the question is, write down all the elements and their orders. Good. Okay, so it means we have to write down all the 2x2 matrices with entries in this field and figure out which ones are invertible and which ones are not invertible. And then we kind of go from there. Okay. Okay, well, one that I know is invertible is the identity matrix.
One is enough.
Okay, so let's start with that one.
Here's a result from search.
Sorry. That's annoying. Okay. Okay. Okay, so let's start with the identity matrix. I'll let I. This is in GL2F. Since we have to do diagonal times diagonal minus off diagonal times off diagonal. Okay, so since the determinant of I, that's just 1 times 1 minus 0 times 0, which is 1. Not equal to 0. Okay. What about, okay, so that's one possibility. Okay. We should try and go about this in a systematic way, I guess. So let's also try. Let's just try and write down all the different matrices we can think of. Okay, with ones on the diagonal. And see what happens there. Okay. Okay, so if we think about it, there's 2 choices for each entry and there's 4 entries. So there's like 16 matrices to go through. And I'll try a couple more and then I'll probably leave the rest for you. Of course, there's like a matrix like this. Then we could also try a matrix like that. Okay, and then I'm missing, you know, I have written down 6, there's 10 more. Okay. So let's compute the determinant of each one. So 1 times 1 minus 1 times 0, that's 1. So here we have determinant equals 1. Here we have determinant equals 1 times 1 minus 0 times 1. That's 1. Here we have the determinant is 1 times 1 minus 1 times 1. That's 0. Because we don't have to worry about that one. Here the determinant is 1 times 0 minus 0 times 1. That's 0. Don't have to worry about that. Here the determinant is 0 times 1 minus 1 times 1. Oh, the determinant is -1. We're in Z mod 2Z. And so -1 is just 1. That's because 1 plus 1 is 0 mod 2. So if 1 plus 1 is 0, then -1 is really 1. Okay. So now what we want to do is look at these 4 things and compute their order. That means we need to find a power, which when I raise it to that power, I get the identity. Of course, here's the identity matrix. The smallest positive power which I can take is 1, right, to get the identity matrix. Okay. So let us just remember what the order is. O of G is just the least positive integer n such that G to the n equals the identity. Okay, so the order of the identity matrix is 1. For all the other matrices, we have to kind of square them, cube them, and so on until we get the identity matrix. Okay, so the order of this one is 1. We have to compute the orders of these 3. So let's move on to the next page for that. Okay, so let's try this one first. Let's call this A. And now let's do A squared. We just do regular matrix multiplication, except our coefficients are mod 2. So we just keep that in mind. So anyways, when we do regular matrix multiplication, we have 1 times 1 plus 1 times 0. That's 1. And then we have a 0, and then we have 1 plus 1. 1 times 1 plus 1 times 1. That's 1 plus 1, that's 2, and 2 is 0. And here we have 0 times 1 plus 1 times 1, that's 1. So that is the identity matrix. Okay, so the order of A is 2, since A is not equal to the identity, but A squared is the identity. So the least positive integer, such that A to the n is the identity, is the integer 2. Okay, so there's a question. Can we choose A to be any of the matrices with determinant not equal to 0? That's a good question. So in the statement of the question, we have to do this process for all of the matrices with determinant not equal to 0. So it's not about can you choose A, you have to choose A to be that and all of them. Okay, so okay, so are you asking if you can just write this? Do we need to write the since part? Well, if I write it like this, it just says, if I read it out, it says, order of A equals 2, A not equal to I, A squared equals I. So are you telling me that since the order of A is 2, A is not equal to I, and A squared equals I? Or are you telling me that order of A, that like, you're just writing down facts? And it's not, oh, can you just write order of A equals 2? Yeah, I mean, that's fine. Yeah. Okay. The other 3 or the other 2 were this matrix and this matrix. Okay, actually B is very similar to A. Like B is just A transpose. So B squared is just going to be A squared transpose, which is going to be the identity. So this is similar, so I'll skip it. It's going to end up having order 2 as well. So now let's try C. C squared. We compute, and we see this times this is 1. This times this is 1. This times this is 1. This times this is 0. That's C squared. Okay. Well, now we have to compute C cubed. There's a C times a C squared. Okay, and then we get this times this is 1, this times this is 0, this times this is 0, this times this is 1. Okay, so now we see that the third power of C is the identity and the lower powers are not the identity, so the order of C is 3. Okay. And then so that kind of takes care of you know, 4 matrices. I'll just tell you that in fact GL2F has 6 elements. Okay, so you're just missing we've done 4, you're just missing 2. Okay.
No.
Okay. So I'll leave you to find the other 2 elements and compute their orders. Okay, we should also do a question like question 3. Should do a question like question 3. Okay, so let's work. So let's, instead of just doing question 3, let's just do an example. This is going to be similar to question 3. Okay. Let's look at in Z mod 27Z times, or let's compute the orders . 1 bar, 2 bar, 5 bar, -2 bar, -5 bar, and maybe something else like 17. Okay. And maybe one more, why not? Let's try also 10. Okay. Solution. So the elements of this group are all the congruence classes, mod 27, that share no common factors with 27. So basically they can't have any 3s in their factorization. Okay. So we can start out with 1, that's the identity of this group. So 1 bar to the power 1 is 1. So we can say that the order is 1. Okay, and that will always happen for the identity, so we can kind of take care of that. What about for 2? Let's try 2. So maybe it's better to have a table or not, but so we consider 2, then 2 squared, that's 4. 2 cubed, that's 8. So far these are not the not congruent to 1 mod 27. 2 to the 4th, That's 16. 2 to the 5th. That's 32. Now we can reduce mod 27, right? 32 when you divide it by 7 as a remainder of 5. Okay, just keep on going. 2 to the 6th. That's 5 times 2. That's 10. 2 to the 7th. That's 2 times 10. That's 20. 2 to the 8th. That's 2 times 20, which is 40. Mod 27 is 13. Now 2 to the 9th. That's 13 times 2, that's 26. Okay. Let me try and give myself some more room. Now, here 26 is really -1, mod 27. So it turns out there's actually a trick you can do here, but I will just ignore the trick and just continue on. So 2 to the 10th. Well, that's just -1 times 2, so that's -2. 2 to the 11th. Well, I guess we can rewrite -2 as 25. 2 to the 11th is, -2 times 2, that's -4. All right, so what we're going to see is this same sequence, but multiplied by -1. Okay, and so -4, that's just 23. To the 12th, that's going to be -8. In other words, 19. To the 13th is going to be -16. In other words, 11. To the 14, that's going to be -5. Right. I'm just going along the same thing I see, but multiplied by -1. So that is 22. To the 15th. Right. So the next one was 10. So this would be -10. In other words, 17. To the 16th. What's that? The next one is 20. So there's going to be -20. In other words, 7. To the 17th. It's going to be -13. In other words, 14. To the 18th is going to be 28, which is 1. Okay, and you notice we didn't see 1 before this. Okay, so the order of 2 is 1. Or sorry, it's not 1. It's the order of 2 is 18. And actually, if you go through this list, actually every integer that's co-prime to 27 occurs. Okay. So in fact,
Sir,
yes.
I have
There's
a question. By 2 to the 14, right? The in front of 2, is that a summation sign? So after -5 equals, that is a summation sign on 2?
No, that's 22.
That's 22. Okay, thank you.
Because 22 plus 5 is 27.
Okay.
27 is really 0. Because we're working mod 27.
Okay.
Okay,
Thank you.
no problem. Okay. Oh, I see. Now I see that it does look like a summation sign. But it's really supposed to be a bar above and then 22. Now I really see that it was a summation sign. Sorry about that. Can you just use the calculator and put the answers? I mean, I guess so, but if you write your working and it's and you like make a typo or something, then I can see what you were thinking. I can mark accordingly. If you make a typo in your calculator and you just write down the wrong things, I can't give you anything for that. So it's really up to you. I guess I would suggest if you do that to double check. So yeah. Okay. Any other questions? Okay. So what I wanted to mention was that this group that we're working with, Z mod 27 cross, this is a group with 18 elements. So if we compute 527, this is our Euler phi function. That's just phi times 3 cubed. Our formula for phi. Yeah, so there's a question, does it make more sense to just check orders as divisors of the number of elements of the group? Yes, it does. Of course, if we don't know how many elements are in the group, then we can't do that, but we're now about to see how many elements there are. But that is a good point. Let's try and explain that now. Yeah, of course, it's like pretty tedious to check to compute 18 powers, but okay. So first, let's remember the formula for the Euler phi function. Well, the formula says, let me just remind you of the formula. Phi of p to the a, where p is prime, is just p to the a minus 1 times p minus 1. So phi of 3 cubed is just 3 squared times 3 minus 1. That's just 9 times 2, that's 18. And phi of 27, that's the number of elements of this group. Oops. This is a 7. This is the integers cross. Okay. So there are 18 integers between 1 and 27, which are co-prime to 27. And if I look through the powers of 2, I got 18 different powers of 2. In particular, everything in this group can be written as 2 to the something. Okay. Okay, so this tells us a couple things. One, it tells us that Z, well, 27Z cross is a cyclic group. Two, since G to the 18 equals E for all G in our group Z mod 27 Z cross, oops, sorry, I went down too far. Okay, since we have this, since there are 18 elements in Z mod 27Z, cross G to the 18th is the identity. Well, the identity is really just one bar. Okay, now since G to the 18th is the identity, in fact, the possible orders have to divide 18. So the possible orders of G, well, you have, it could be order 1, it could be order 2, they just come from divisors of 18. Let's see, we have 3, we have 6, 9, and 18. That's it. So what I really should have done was just, I should have checked yeah, so that would of course be much more efficient. Yeah. Okay. So, right, so let's explain what we should have done. We should have just, we know that 2 to one of these, like we know one of these things is the order of G. Okay. In fact, there's like several tricks you can do, but what we should have done is we should just check, is G the identity? Yes or no? Is G squared the identity? Yes or no? G cubed is the identity? Yes or no? G to the 6th is the identity? Or G to the 9th is the identity? Okay, and as soon as we answer yes to one of these questions, we can stop. Like if G squared is not the identity and G cubed is, then 3 is the order. So let's keeping in mind these are the possible orders. Let's try our next example, which was I think the number 5. So let's try for 5.
Excuse me,
Yeah.
I have a question. What is the difference between Z/27Z and 27Z?
Okay. Let me try and write down your question. So we have Z, 27Z, and then you also have 27Z. These two things?
Yes, sir.
Okay, that's a good question. Here we have the congruence classes of integers mod 27. So an element might be like 3 bar, which is a congruence class mod 27, which means it looks like it's a set of integers. This one is like a bunch of them, so it's maybe like 20 minus 24, 3, 30, 57, and on and on. Okay, 27Z is a particular congruence class. It's just the multiples of 27. So you have minus 54, minus 27, 0, 27, 54, and on and on. Good. And another way to think about it is 27Z, that's a subgroup of the integers. And then when we do Z mod 27Z, that's the quotient group. Okay. And then what we're talking about in this question is Z mod 27Z cross, which one way to think about this is the congruence classes such that the GCD of N and 27 is 1.
Okay, sir.
Okay. Okay. So